This video is on solid of revolution, and what I have here is a yellow region right here, and I'm going to revolve it about the x-axis, and then we get a solid of revolution, and then I want to find the volume. In a previous video I did the same problem, but we found the volume of the solid by using the definite integral. In this video I'm going to show how to find the volume of the solid without using the definite integral. And here, once again, this is the region that we want to revolve. And this region right here is bounded above by the graph f of x equal to 2 times the square root of x. And it's bounded below by the x-axis from 0 to 9. And so let's revolve this region right here about the x-axis. And this is our solid of revolution, and we want to find the volume of this solid of revolution. And the way we find the volume of the solid of revolution is by dividing the solid right here into many slices, thin slices like this right here. And then each slice would be in the shape of a cylinder. And then we would find the volume of each cylinder and then add all the volumes together, and then that will give us an approximate volume for the solid. And so one of the slices or one of the discs would look like this. And so let's go find the volume of this disc right here. Let's call it the ith disc. Notice that the distance from here to here is 9. And so if we divide the solid into 9 discs or 9 slices, then the thickness of each disc will be 9 over 9, which is 1. But if we divide the solid into 90 slices, then the thickness of the disc will be 9 over 90, which is 0.1. And so in general, if we divide the solid into n number of slices, then the thickness of each slice will be 9 over n. And so let's denote the thickness of each slice as delta x. And what I want to do next is this. If I'm going to divide the interval from 0 to 9 into n number of sub-intervals. And then the value right here, let's call it x of 0, and then x of 1, x of 2, x of 3, x of 4. And then eventually we'll get to x of I minus 1, and then x of I, and then all the way over to 9, which is x of n. And so the thickness of this disc right here, earlier we denoted as delta x. And so from here to here would be delta x. And then from here to here would be delta x, delta x, delta x, and so on. And so we look at x sub 0, which is just 0. And then x sub 1 is just 1 times delta x. But delta x is 9 over n, and so we get x sub 1 is 9 over n. X sub 2, which is right here, would be 2 delta x, or 2 times 9 over n. And then x sub 3 would be 3 times delta x, or 3 times 9 over n. And so in general, for x sub I, we will get I times delta x, or be 9I over n. And so that's x sub I. For the ith disk, the value right here, this is x sub I minus 1, and then the value right here would be x sub I. then f of x sub I would be the distance from the x-axis up to the graph at x equal to x sub I. But notice that f of x sub I is also the radius of this ith disk. The volume of this ith disk or ith cylinder is pi times the radius squared times the height. And so the radius of this cylinder is f of x sub I and then squared. And then the height of this cylinder would be the thickness of the cylinder. But the thickness of the cylinder, we call it delta x. And so the volume of this ith disk would be pi times 2 times the square root of x sub I times delta x, since the f of x is 2 times the square root of x. And so this is the volume of the ith disk. If we have n number of disks or n slices, then the volumes of n slices would look like this. This would be volume of the first or disk number 1, volume of disk number 2, and then this is volume of the nth disk or the nth slice. Using summation notation, then we would have I running from 1 to n. And then notice right here, 2 times the square root of x sub I squared would be just 4x sub I. And so this is the volumes of n number of slices, and therefore the volume of the solid of revolution will be approximately this summation, this sum right here. Now, if we want the exact volume of the solid of revolution, then we have to we have to divide the solid into an infinite number of slices, meaning we have to allow n to run to infinity. And when n approaches or runs to, when n runs to infinity, then normally we write it like this. It'd be the limit of this sum right here as n approaches infinity. And then, as I mentioned earlier, when this limit right here exists, then we defined it as this definite integral right here. And then in the previous video, I've shown that the value of this definite integral is 162 pi. But in this video, let's find the value of this quantity right here, limit quantity, without using the definite integral. And so a few moments ago, we saw that x sub I is just 9I over n, and delta x, or the thickness of each disk, is 9 over n. The volumes of n disks will be pi times 4 times x sub I times delta x. But x sub I is 9I over n. N is the number of subintervals or the number of slices. And then delta x is 9 over n. And so we get 4 pi, and then this would be 81I over n squared. The summation here is with respect to I, and therefore we can move the 81 over n squared and place it in front of the summation. And then recall that if we have the sum of 1 plus 2 plus 3 all the way up to n, and then it's n squared over 2 plus n over 2. And therefore this sum right here is n squared over 2 plus n over 2. And then simplify, we get 81 over 2 plus 81 over 2n. And so this is the volumes of n slices or n disks. The volume of the solid of revolution, that's where we divide the solid into an infinite number of slices. And so we have to allow n to run to infinity. And so this would be the volume of the solid of revolution. But this quantity right here is 4 pi times 81 over 2 plus 81 over 2n. As n approaches infinity, 81 over 2n approaches 0. And what's left is 4 pi times 81 over 2. And so we get 162 pi, which is the volume of the solid of revolution. And so we just got the volume without using the definite integral. And that's the end of the video.